Okay, so if you have not logged into Pear Deck yet, please go ahead and do so. The code is up here as well. How I wanted to start today, though, is I wanted to go back to a problem that we did half of on Friday and start by doing the other half of it today. So we ended with this one, we did all of the purple calculations at the end of Friday's class. Let's take our first 5 or so minutes today and try to do the calculations here in one. And so again, I'll leave this up for you. Make sure you get your calculators out and remember those calculations that you can do. We're using that calculation box. So how do you turn hydroxide into hydronium? How do you turn those things into pH and POH? That's what you're being asked to do here with the white colored examples. So 5 minutes, try to get as far as you can. I'll be around to see how you're doing. So for trying to figure out how to do this, what you need is a starting point. You need to know somewhere to get your calculations rolling. And then it really becomes a matter of just knowing what calculation do I do when. And so this calculations box can be really helpful for that kind of thing, because it can tell you all of the different relationships that exist between these 4 different measurements. And so since we're starting with hydroxide, there are really 2 ways that we can go. One way we can go is I could use this top equation to turn the hydroxide into hydronium, so solve letter F, by doing that calculation that we did a number of times last week. So hydronium concentration would be equal to 1 times 10 to the negative 14 over the hydroxide concentration, 4.5 times 10 to the negative 8 molar. And if I do that, 4.5 times 10 to the negative 8. I get 2.2 times 10 to the negative 7. Now, maybe that wasn't your first thought. Maybe your first thought was, hey, I've got a hydroxide concentration. Why don't I turn that into POH? You could do that as well. POH is equal to the negative log of 4.5 times 10 to the negative 8. And if I do that, I get 7.35. Now I've done 2 of the calculations. I could use either result to figure out the 3rd calculation. I can take that hydronium, take the log of it, get pH. That would be one way. The other way is I can just use this 14 relationship. pH plus POH is 14, and naturally come up with the fact that the pH has to be 14 minus this. So the pH must be 6.65. If I had taken the logarithm of 2.2 times 10 to the negative 7, I would have got there as well. I would have got 6.65 in that calculation as well. So This is kind of the beauty of this particular calculation box approach, is that there are multiple ways of getting to the same result. It really just becomes a matter of, if I had a problem like this, all I need to do is identify what I know, and then just identify which of these equations I could use to get me to what I'm trying to find out. So if I'm giving hydroxide concentration, what am I being asked to find? Being asked to find the POH, okay? Take the logarithm of it, I got my POH. Am I being asked to find the pH? Okay, I can find the POH, turn it into pH pretty easy. This is basically the essence of this chapter in terms of calculation stuff. Now, in a second here, I'm gonna give you one last concept out of this chapter, just to kind of tie things up. But from a calculation standpoint, again, we're looking ahead to next Wednesday, Wednesday's exam, this Friday's quiz. This is the kind of calculation that you need to know. The other kind of things that are discussed in chapter 14 are titrations, but guess what? We already did titrations in chapter 13. Your book called it Solution Stoichiometry. It's the same calculation. You just use the titration equation. You gotta make sure you have a balanced chemical equation. Any questions with this example? Either side, Friday side or the Monday side, before we put this one away and focus on that last concept in the chapter. Okay. When it comes to measuring pH, have any of you looked, what lab are you doing today, tomorrow? That's a pretty deafening silence right there. Okay, so one of the things that you're going to be doing is you're going to be using test strips and litmus indicators to help you identify acids and bases. And that's what these are dyes basically that are pH sensitive. So pH goes up to a certain level, it changes to one color. If it goes down to a certain level, it changes to a different color. Now, there are lots of different kinds of applications. You know, on the left there is a pH meter. pH meter would be kind of the most raw, quantitative way of doing it. It's also the most difficult way of doing it. And honestly, you're not going to see a pH meter until Chem 106, at least if for those of you that have to go that far in your studies. Chances are pretty good that we need to know the pH of something. We need to know it more qualitatively. And so we're going to use test strips. Test strips like the ones in the middle. If you have a pool or hot tub, you've probably seen something like that. It's basically it's a multi-test water quality strip. Tells you a whole bunch of information all at the same time. It's all related to the color changes. Tells us the pH, tells us the acidity, tells us the alkalinity, tells us the hardness of the water, along with a whole bunch of other stuff. Which again, if you're dealing with a pool or a hot tub, it's kind of stuff that you want to make sure you know so that you're not accidentally exposing yourself or others to a whole bunch of nasty stuff. But at the same time, doesn't do a whole lot for you otherwise. In the laboratory, we tend to use chemical indicators. Now, this is an example of the chemical indicator that you'll use. This indicator is called phenolphthalein. It is a mouthful. It has many, many letters. But the important thing for us, as far as phenolphthalein is concerned, is that in acid, it appears colorless. In base, it appears to be a magenta kind of color. Where it gets used most often is in a titration kind of situation. And in the titration situation, since we are looking for neutralization, we're looking for somewhere near pH 7. And at pH 7, this phenolphthalein indicator actually takes on kind of like a rose pink kind of color, as opposed to that brighter hot pink magenta kind of color. It's kind of an in-between state. Colorless is acid, base is magenta bright pink, and the midpoint of that titration is kind of like a rose color. Just like very soft pink. And that gives us an idea of when we're doing a titration, how far does that titration actually need to go? The actual chemistry of it is kind of cool. Colored substances like dyes usually rely on a network of single bonds and double bonds to help them to resonate a particular color from an electronic standpoint. If we break that pattern, like has been done here, the color goes away. And so what you'll find is that a lot of indicators, a lot of chemical dyes follow that kind of patterning. So with phenolphthalein, it's colorless and pink. In other kinds of indicators, you will see a wide swath of color changes. Anything from something like thymol blue, which can range all the way from red in the extremely acidic sense to blue in the basic sense and yellow in between. To, this isn't the most wide variety, but there are actually a number of indicators that will mix multiples of these and give you basically a rainbow of colors. Ranging from red at the extreme acidity side to purple at the extreme basic side. And every color of the rainbow in between as you go from pH to pH. The last concept that we want to look at out of this chapter is something called a buffered solution. Now, buffered solutions, or buffers, are solutions that are naturally resistant to changes in pH. So you can take that solution, expose it to a pretty decent dose of acid, and its pH will not change drastically. Expose it to an extreme solution of base, and its pH will not change that drastically. The most common system that exhibits this kind of behavior is actually your blood. Your blood is naturally pH tempered around pH 7.4. So just a little bit on the basic side of neutral. And in your blood, you have a combination of two things, carbonic acid and bicarbonate ion. Now, what we need to know about those two things, carbonic acid is a weak acid. Bicarbonate ion is its conjugate base. Any solution that contains a weak acid and its conjugate base, both present in significant amounts, will exhibit this kind of buffer behavior. So in your blood, you have roughly equal amounts of carbonic acid and bicarbonate ion. And so this allows you to do things like eat acidic and basic foods, expose yourself to different kinds of environments, and not go into septic shock. So, your average can of soda has a pH of somewhere between 4 and 5. How can you drink that stuff and not immediately go into acidosis? Your blood takes care of it. In higher concentrations of acid, what happens is that the bicarbonate in your blood will absorb that extra acid and turn it into carbonic acid. So instead of the pH changing, what happens is that the ratio of the two substances changes instead. We see instead of a change from pH 7.4 to pH 4.4, you see a change from 7.4 to maybe like 7.35. It changes just slightly. It does get more acidic, but not nearly to the same degree. And if you were exposed to a high concentration of base, why doesn't that hurt you in the extreme either? Same thing. The base reacts with the carbonic acid to make bicarbonate, to make its conjugate base. Instead of your pH fluctuating wildly and going into alkalosis, the ratio changes and you end up with more bicarbonate in your system compared to carbonic acid. But the key feature here, this is not just unique to your blood. Any system that contains a weak acid with its conjugate base will exhibit this kind of behavior, this pH resistance. This is also why certain products like bufferin exist. Bufferin is a buffered acid aspirin supplement. Why does it exist? Well, aspirin is an acid, and in some people, it can irritate their stomachs because of the extra acid. So, you know, someone who has a really high sensitivity to acid, maybe they suffer from GERD or from acid reflux or other kinds of gastrointestinal distresses. Aspirin can be really hard on them because the extra acid can irritate their stomachs. But what bufferin does is it adds a buffer, it adds salicylate to the aspirin, and it basically doesn't negate the acidic effects, but it definitely mitigates them so that it's safer on their stomachs. All right, one final question for us as we close out for today. I've got 3 different systems on the board. Which of these can act as a buffer All right, we're getting in, most of us are getting something in. We seem to be falling on one answer in particular, although a couple of others are getting some response as well. Let's break it down. To have a buffer, I have to have a weak acid and its conjugate. So, number one, do I have either in the case of number one? Hydrochloric acid is a strong acid, so right away we can eliminate it based off of that. But we're also missing the conjugate. The conjugate would be fluoride, and there's no fluoride in the other substance. So we're missing the weak acid. We're also missing the conjugate. Neither are present. Number one, that would be a neutralization reaction. We would get sodium chloride and water when those two things come together. In number two, I have an acid, harder to see because it's written in organic form, but this is basically acetic acid. Written up a little bit differently because it's written in its organic format. Acetic acid is a weak acid. And the thing that we should be able to pick out and notice is that with this compound, I can see that there is a common thread. The CH3CO2 is common to both substances. The only difference between them is a hydrogen. Wait a second, that sounds familiar. That's the exact definition of conjugates. Conjugates are two compounds that are essentially the same, but separated by a hydrogen. So here I have a conjugate pair. I've got a weak acid, I've got its conjugate base. Number two is definitely a buffer system. This would be the acetic acid acetate buffer system, which is another column. Now in the third one, I do have a conjugate system. HBr and NBr are separated by each other by only a hydrogen. So they are conjugates. But they're not a weak acid conjugate system. HBr, hydrobromic acid, is a strong acid, not a weak acid. So since it is a strong acid, it cannot be a buffer. So the correct answer here was the answer most of you came up with, which was number two. Number two and number two only would be the buffer system here. Right. Any questions about this one? Okay. So get your last participation point for today. I'm not going to try to open up gases here in the next 2.5 minutes. So we'll just leave it here at that. So your only assignment between now and Wednesday is to work on that post-lecture 14.3, assignment 14.3, which is basically what we did today. Review those calculations and look at buffers. And if you're looking for something else to do and you haven't done your critical thinking assignment yet, that'd be a great thing to do. Have a good day. I'll see you on Wednesday. Question?